Hey everybody, I hope this won't take too long, so let's just get into it. The circuit practice sheet that I gave you. So hopefully this will sort of get you to know if you're kind of ready for what we're going to be doing next week, because we are going to be doing some complicated circuits as we go through next week and you build them. So let's look at the first one. Just kind of forgive me because I can't erase on this, so if I do any mistakes, I'm going to have to just scratch them out. But my total voltage on this is going to be 9 volts. Yeah, it's really thin, this scribbling, but I'm sure you guys can figure it out as we go. The total resistance on here is 2 ohms plus 3 ohms plus 1 ohm. And last time I checked, 2 plus 3 plus 1 is 6 ohms. Oops, 6 ohms. And therefore, using the equation V equals IR, we're going to do 9 volts equals I times 6 ohms, which is the resistance, and 9 divided by 6 is going to give us a current of 1.5 amps. Okay, so I hope you're with me so far. And we know that that 1.5 amps goes through all three of those resistors, 1.5 amps, and I3 is 1.5 amps. And we know the resistor R1 is 2 ohms, R2 is 3 ohms, and R3 is 1 ohm. So if we use V equals IR again, V equals I 1.5 times 2, we're going to end up with 3 volts lost at resistor 1. We're going to end up with 4.5 volts lost at resistor 2. And we're going to end up with 1.5 volts lost at resistor 3. Again, we're just using V equals IR. And if you add 3 plus 4.5 plus 1.5, you should end up with the full 9 volts. Now we get into the fun ones. All right, so this is a complex circuit. And the first thing I want you to realize is that we do have 20 volts coming out of the power supply. And the next thing we need to do is figure out the total resistance. And I told you last week how we can turn a parallel piece into sort of a series piece where we can figure out, well, 5 ohms and 6 ohms in parallel, we can figure out what they actually make if we combine them and how they act. So the equation to do that is 1 over R1, which is 5, plus 1 over R2, which is 6. That equals 1 over the R total. And if you take that, you would end up 1 divided by 5 plus 1 divided by 6, you're going to get a number. And you take the inverse of that number, and the inverse of that is going to be 2.727. And I'm going to try as often as I can to take this out to 3 decimal places, just to keep everything kind of clean. I remember last time we did this, it wasn't very clean in terms of the totals, but I think this will be working better if we keep everything to 3 decimal points. So we have these two which combine and act like a 2.727 ohm resistor, and they're in series with a 3 ohm resistor. So if we're looking at our total resistance, we're dealing with 2.727 plus 3, because they're in series with each other, and you should end up with a total resistance for this particular circuit of 5.727 ohms, okay? And now we got a 20 volt battery with a 5.727 ohm set of resistors, and that's going to give us a current, V equals IR, of 3.492 amps, okay? And this is, I'm hoping you're kind of getting this, and if you see that, take a second and go back and calculate it out. And now we can we can look at this and say, well, I don't really know what's going on over here, but I do know that all of these currents, all the current is going through R3. And R3 is 3 ohms. And I know that all the current, all 3.492 amps of it, is going through that because there has no choice. So if we multiply V equals IR, if we multiply I and R, we should end up with V3 being 10.476 volts. So that's how much we lose here. And if we start with 20 volts, that means that we have to lose the rest of it at either R1 or R2, which means V1 and V2 are going to be identical. So if we take 20 and we subtract 10.476, we should end up with a little over 9.5. So I'm going to round 9.52 just because of how I did my calculations. 9.52 volts at both V1 and V2. Okay, so that's kind of where I ended up with the V1 and V2. We already know that R1 is 5 ohms, and we know that R2 is 6 ohms. And again, using V equals IR, I have a V and an R. I should be able to figure out my I, and my I for resistor 1 is going to be 1.9 amps, and for I2, if you do it out, it's going to be 1.588 amps. So I hope that kind of makes sense. And the cool thing is, all right, let's pretend that you didn't do 20 minus 10.476. You didn't think about that to get V1 and V2. You could also do it by knowing that all of the current is going through whatever the equivalent of this is, which is 2.727 ohms. So if you actually did total current, which is 3.492 amps, and you multiply it by the total voltage, or I'm sorry, the total resistance here, which is 2.727 ohms, you would actually come up with just about 9.52 volts. So 3.5 times 2.7 should give you about 9.5 volts, which is what you lose either if you go this way or if you go this way, which is really what you lose when you just go through this thing that you sort of imagine is there, this particular resistor. So that's how you actually sort of have to start thinking about these, looking at the voltage going through the total resistance of a parallel piece. The only way you can attack the back of the sheet is if you do that. So we didn't need to do it here because I knew what I lost here and I could take whatever was left over and lose it here. But if you flip over the sheet, we've got this situation where now I have to figure out how much voltage I'm losing here and how much voltage I'm losing here, and you can't do that nice subtraction trick. So let's try and work this through. It's actually, the math is very simple. It's a little more difficult to really visualize, but hopefully I'll be able to do that with you. So for this one, again, 25 volts because we know that's what my voltage is. I have no idea what my total current is, but I can figure out my total resistance is by doing the 1 over R1 plus 1 over R2 for this, and I'm going to imagine the equivalent resistance for this piece too, which is 1 over R3 plus 1 over R4. So for this, 1 over 2 plus 1 over 3 gives me 1 over my R total. Okay, so 1/2 plus 1/3, I'm going to get a number, and I'm going to invert that. And that should give me this thing, which is 1.2 ohms. And for this, 1 over 5 plus 1 over 3 is going to give me 1 over R for this piece. So 1 over 5 plus 1 over 3 is going to give me a number. And then I'm going to invert that number, 1 over whatever that is, and that should give me 1.875 ohms. Well, this and this are in series. And how do I work with series resistors? I just add them to figure out the total resistance. So 1.2 plus 1.875 should give me a total resistance of 3.075 ohms. And from there, 25 equals I times R, V equals IR. If you divide 25 by 3.075, you should end up with a current of 8.13 amps. Now, this is crazy because we've never really seen a current this big, but, oops, that's not 18, it's just 8. We've never seen a current this big, but we have 2 sets of options for those electrons to go through. So that's kind of why this is so large. So now we got to figure out what's VI and R in all of these resistance, or all of these pieces of this crazy parallel circuit. Well, the R's are simple because we have them. R1 is 2 ohms, R2 is 3 ohms, R3 is 5 ohms, and R4 is 3 ohms. So that part's easy. What we got to do now is figure out what's going on with my voltages. Because I know that my total current is 8.13 amps, but I have no idea how much is going through this, or this, or this, or this. But I can sort of think about it like, well, all right, I know 8.13 amps has to go through this 1.2 ohm resistor. Even though it's not really there, this branch is acting like a 1.2 ohm resistor. So if I do V equals IR, with the V being what I'm looking for, my current, I know that's 8.13 because all of the electrons have to go through both of these. So, and they're both acting together like a 1.2 ohm resistor. So I hope that kind of makes sense. All the electrons are eventually going to get through what's acting like a 1.2 ohm resistor. And that means that both the voltages, they got to lose the same amount of energy in both resistors. And we sort of talked about that last week, but this is where we're really going to sort of apply it. So the voltage for both of these is going to be how much energy they lose basically in a 1.2 ohm resistor. And if we do that, 8.13 times 1.2 ohms, that's an ohm, you should end up with 9.75 volts. Harry Potter scar, not really. 9.75 volts there, and for V2, again, 9.75 volts. And the same thing can be done here. I know that I know that 8.13 amps is going through R3 and R4 together. And I know that R3 and R4 are acting like a 1.875 ohm resistor. So if I multiply the current times the resistance, I should end up with a voltage. And for these two, we're going to end up with 15.24 volts. So at V3, 15.24 volts. And at V4, 15.24 volts. And the crazy thing is if I add any path, 15.24 volts here or here, and 9.75 volts here or here, the electron's going to have to lose 25 volts no matter how I go. 9.75 this way, 15.24 this way, and then we're down to 0. And if I go the other way, still 9.75 and 15.24. So no matter what, the electron's going to lose all of its energy across all of those resistors. So now it's just a matter of, well, I have a V and an R, can I figure out the I? I have a V and an R, can I figure out that I? I have a V and an R, can I figure out that I? And I have a V and an R, can I figure out that I? And this is just a matter of dividing, the voltage divided by resistance will give you the current. And for this, 9.75 divided by 2 is going to give you 4.875. 9.75 divided by 3 is going to give you 3.25. 15.24 divided by 5 is going to give you just about 3.048. And 15.24 divided by 3 is going to give you 5.08. And here's the crazy part. If I add these two currents, 3.048 and 5.08, I get a little over 8. And if I add these currents, 3.25 and 4.875, I get just over 8.13 amps. So you see the current stays constant even though it gets broken up. They all add up to 8.13 amps. So I hope this is sort of making a little bit of sense. And the last one, we can use the same logic. We're going to start out with 30 volts. Let me get all the way down the bottom here. 30 volts. And we're going to figure out what this piece is. 1 over 10 plus 1 over 3 equals 1 over R total. Okay. And that piece here should end up being 2.307 ohms. And that is now in series with a 3 and a 3. So 3 plus 3 plus 2.307 is going to be 8.307 ohms. Okay, so now I got 30 volts, I got 8.307 ohms. I can now do V equals IR, and hopefully I would end up with 3.61 amps. And now again, I'm just going to go through and plug in what I know. My R1 is 3, my R2 is 10 ohms. My R3 is 3 ohms, and my R4 is also 3 ohms. And now I can actually say, all right, cool. 3.61 amps is going through R1 and R4. So I1 is 3.61 amps. And I4 is also 3.61 amps. Because I know there's no choices here. Now I've got I've got R and I, so I can figure out V. So 3 times 3.61 should give me about 10, oh boy, I can't write, 10.83. And then V4, 3 times 3.61, that's going to be also 10.83. And I hope that would make sense because it's the same current and the same resistance for both of them. And now we just have to figure out what we're losing in V2 and V3. Now you could do it either by saying, I know all 3.61 amps is going through a resistor that's equivalent to 2.307 ohms, and you would get a current that way. I'm sorry, not a current. You would get a voltage that way. Or you could say, all right, I started with 30. I lost 10.83 here. I lost 10.83 here. So what's left for me to lose here? Now the cool part is, either way you do it, you should end up with 8.32-ish volts. So between V2 and V3, you're going to lose 8.32 volts. Okay, so if I'm an electron and I go this way, or I go this way, I'm going to lose that 8.32 volts. So now I have R and V, now I can figure out I. And now I have R and V and I can figure out I. So at V2, or at the resistor 2, 8.32 divided by 10 is going to give me a current of 0.832 amps. And at resistor 3, I've got 8.32 volts and a resistor of 3 ohms. So my current at R3, which is the current I3, that's going to give me 2.77 amps. And the fun part, 2.77 plus 0.832 should give us 3.6-ish amps, which is how much is going through this whole piece. So I hope that made sense. I hope the explanation was good for why we can sort of use that 1 over R total thing to our advantage to figure all this stuff out. So we'll pick this up on Monday. If there's any time left over in class, please start thinking about the wiring diagrams for your games that we're going to be building next week. I got all the cool equipment in. I got some copper tape and I got the LEDs, so we're going to make this all happen next week. Okay? Can't wait to see you then.